Welcome back to this course on C programming and assembly language. In the last lecture, we looked at how we could pass variable number of arguments to printf and yet have the function execute without any error. In this lecture, we will now look at how to implement printf, and particularly we will look at the implementation of two functions va start and va arg. Instead of looking at trying to write this from scratch, we will just look at what implementation we have here. We will look at the assembly output of the two functions. So, you have the va start, right, and that translates to these two functions, right. Let me write that down separately so that we can, So, va start. Okay. What does this translate to? It translates to LEA. I will tell you what that instruction is, right. LEA EAX comma underscore FMT of EBP plus 4 okay, and then I am going to simply move D word PTR underscore AP of EBP comma EAX. Okay. So, before we proceed, let me clarify what this particular thing means, right. This essentially is simply going to translate to I think there is a dollar also, FMT dollar and AP dollar. Okay. This simply is going to translate to contents of EBP plus underscore AP dollar, right. So, this is just D word pointer of EBP plus underscore AP dollar. Now, what is underscore AP dollar? That is a constant that is defined on top of the program here, and you see that that is nothing but EBP underscore AP dollar is -8. So, this guy is equal to -8, and therefore, this is nothing but contents of EBP -8. That is how you are supposed to implement interpret this particular mnemonic, right. So, all you have to do is take that constant and just add it into the contents of EBP plus something, right. Now, let us look at what this function is doing. Okay. So, for that, let us look at the picture of the stack when we invoke function, when we invoke printf in the following way, right. I am going to say double equals %f int equals %d and x comma n, right. So, what would happen? We said that the assembly implementation is push n, push x and then push pstr, right. So, the stack is going to look like this. Okay. So, I will push 4 bytes, which is n, onto stack. Okay. Then I am going to push 8 bytes, which is x. Remember, x is a double, right, and this is 8 bytes, this is 4 bytes. Then I am going to push pstr, okay, the constant string which is pointing to that. This is pstr is this particular string, and then I am going to call printf, or I am going to call the function myPrintf, which is okay. So, what will happen is the return address, right, will essentially get stored. So, you will basically invoke this and say return address and the moment you enter the function myPrintf, the prolog will get executed, which is basically push EBP of the caller onto stack, move EBP to ESP, right, and then subtract ESP with some value, right. So what happens is EBP of the caller will get pushed onto stack. Okay, and after this my EBP will be made to point here. So this we already saw in the earlier lectures, and of course my ESP will be pointing to some location here, right. So in this example it says subtract ESP comma 24. So this distance would be 24. Right. So now let us look at what this LEA EAX comma underscore FMT of EBP plus 4 is. So what does this particular thing translate to? First of all, let's go and look at what underscore FMT dollar is. It is 8. So this is nothing but contents of EBP plus 4 plus 8. Okay, which is EBP plus 12. Okay, so if this is EBP, this is EBP plus 4 plus 8 plus 12. So this is where my argument pointer is getting initialized to, right. So this is EBP plus 12. So why are we initializing it there? Because you need to initialize it to after the char star pointer, right. The arguments start after the char star pointer. So you are going to initialize it to something after that, right. Now what does this LEA EAX comma something do? It loads the effective address onto this register, which means that this particular thing is load EAX, right, and it's a address. So the contents of will go and whatever address remains will get loaded into the EAX register. It will simply get loaded with EBP plus 12. That's what the load effective address instruction does. And the next instruction, move dword pointer comma AP underscore AP of EBP, is to simply assign AP with the value that has been calculated, EBP plus 12. So now my argument pointer variable has got initialized to the right value, so that I can start reading out these values as and when I encounter them. So remember now, upfront I do not know if the data that is pointed to by EBP plus 12 is an integer or a double or whatever. That needs to be inferred only from the string by parsing it and figuring out if it's a %d or a %f. So now the next thing that we want to do is to look at how you would initialize, how you would implement VA arg macro, right. So we are basically saying we are going to call VA arg of AP comma int, let us say, okay. So what is this telling us? It is basically telling us that the data pointed to by AP is an integer. That means the next argument will be available after 4 bytes, okay. And that is why if you look at the implementation of this particular function here, you will see that let me just get that. So you look for the color, which is ival equal to VA arg V of this, yeah. So you have three things that are being done here, and we'll come to what those three instructions are, right. Normally, if I wanted to access a parameter that is being passed, I would have simply accessed the function parameter as contents of EBP plus some constant. The constant usually is known upfront at compile time, and therefore it is just a register indirect addressing with offset that is used to access that variable. Unfortunately, here the k is now a variable because it depends on what the string is and how the function has been invoked, as given in these three examples here that I just showed you, right. So therefore, I cannot do this register indirect addressing directly because this k is now a variable, and therefore I need to evaluate what this offset is. So how do you evaluate the offset? You just move the variable into a register, add the offset that you want, and then move that new value back into the argument pointer. So if you look at the three instructions that are being implemented here, you have move. So what does this translate to? It's move EAX comma AP. Okay, I am not going to put that d word pointer of underscore AP. Basically, this particular thing simply refers to the variable underscore AP. Okay, I am just moving AP into EAX, then I am adding EAX comma 4. Why 4? This 4 is because I know it is an integer, right, and then I am moving the value back into my AP, move AP comma EAX. So what was being done using a simple register indirect addressing now has to be done in a slightly more complicated way by invoking some registers and ALU operations. That is how, and it is quite obvious that that is the only way you can handle these variable arguments and variable data types when they are passed to these functions. Okay. So after, suppose it were an int, then what would happen is after the these instructions, my AP would be pointing 4 bytes away. Of course, in this case, because it is a %f that we encounter first, note that let me just show you that, right. So yeah, you will note that because the if the argument that was passed was a %f, which is a double, then you will do exactly the similar set of instructions of moving AP into a register, then you will add ECX comma 8. Okay. So if I do 8, then that would be a double. Okay. So in this example, I have DOUBLE equal to, which basically gets printed using this portion of the program. There is no % that has been encountered yet. Then you encounter the first %, and then you check what the type specifier is. It happens to be f, and therefore you now try to access the data from EBP plus 12 as a double, and that is what you are doing here. So after these three instructions, move EAX comma AP, add EAX comma 8 and move AP comma EAX, my AP would be forced to point here. It would have been offset by EBP plus 20, right. So remember, we have still not read the value out into our variable, we have only moved the argument pointer to the next argument successfully. In order to implement the functionality of reading that particular argument into the variable, the following three instructions are executed. Move ECX comma AP, right, and then you do, let's look at the case of the integer so that it's easier. Yeah, okay, and then you move EDX comma D word pointer of ECX minus 4, okay. Then you do move into ival, right, which is D word pointer of ival comma EDX, okay. Now of course, if this happens to be a double instead of an integer, then all the D word pointers would become a Q word, right, Q slash D, okay, and the instead of 4 I would say 8 slash 4. So what we are doing is very simple. The argument pointer, by the way, because of the preceding set of instructions, has already gone to the next argument, right. So therefore, in order to bring it back to read the double or the integer which is the current argument, I need to do this subtraction operation, okay. This is being done because AP has moved to next argument in the previous step, right. So this is how you essentially, what we are essentially doing is we are just calculating the new offset depending on the character string that was passed, going to that location, reading out either an integer or a double or whatever it is, and then we are getting that value into whatever variable we need in order to access, in order to execute this function accordingly, right. At this juncture, I'd also like to point out that instead of an integer, if you tried accessing a character, it is not necessary that you will see a single byte being pushed onto stack. This is because the arguments that are passed and all the memory alignment is done to 4 bytes in some compilers, right. All the memory accesses are aligned to 4 bytes, and therefore even a single byte would actually be sign extended to 4 bytes and then pushed onto stack, and when you access the data, of course you will access it as a byte pointer instead of a D word pointer, right. So I leave this as an exercise for you to implement the %C case and see what happens when you call it with a character instead of an integer, right. I'd like to conclude this lecture by pointing out that it's we discussed that arguments are pushed onto stack from right to left. So the question really is, should I push arguments only from right to left, or can I also do it from left to right, right. So in some sense I am asking, is this just a convention, and was it just a arbitrary choice that the compilers made, that they pushed parameters from right to left? It turns out that the answer is no, this is not an arbitrary choice. You have no choice but to push it from right to left, okay. And why is that? Let's look at again the simple variable argument list passing, right. if I want to do printf of %d, right, comma n, right, then what I will do is we will push. So let me just draw the picture of the stack here. Okay, I am going to push n onto stack, then I am going to push the constant string onto stack, then the return address, then EBP of caller is pushed onto stack, and then my base pointer is made to point here. So now in order to implement this variable argument list, I need to access the char star, right. So the declaration of printf if is char star comma dot dot dot. So this char star I should be able to access irrespective of whether I pass other arguments or not. Now if the parameters are pushed right to left, then the stack gets filled as follows, and PSTR will always be EBP plus 8, contents of EBP plus 8. So there is no issue, I know exactly where this PSTR should be. Now on the other hand, if I chose to push the parameters from left to right, okay, then look at what would happen in two cases, printf %d comma n comma n. Okay, let me just have this kind of a call. Okay, this is pushing right to left. Now what happens if I pushed left to right? Okay, then what would happen is I would first push PSTR, then I would push n, then I would push n again, then I would call printf, right, which means the return address, and this EBP of caller, because the prologue has to be executed like that, and then EBP is here. Okay. Now in order to access PSTR, right, in this case it would end up being at EBP plus 4, 8, 12, 16, right. On the other hand, if I had only a single integer that was pushed onto stack, which is basically case 1 here, 1, 2, right. If I looked at the stack picture pushing left to right for case 1, then PSTR would appear now at EBP plus 12. So what happens is, if I push the parameters left to right in a variable argument list kind of a case, the constant character string will have different addresses with different calls. On the other hand, if I push the parameters right to left, then it is evident that my character string PSTR is always EBP plus 8, whatever happens. It is only the other variables that have variable addresses, which is perfectly fine, because depending on PSTR I know how to actually access those other variables, right. In conclusion, you have no choice but to push the parameters from right to left as we have discussed in our lectures here.